This session will discuss about the crystal field theory. So one of the important topic in this particular coordination chemistry. Here, according to the crystal field theory, if you take a complex compound, the complex compound, if you come across, it is associated with the metal atom or metal ion along with certain fixed number of the ligands. So according to CFT, crystal field theory, the metal ion is considered as a point charge as well as the ligands, that is maybe neutral ligand or the anionic ligand in general, they are also considered as the point charges. So in the case of the neutral ligand, generally it is associated with some more electronegative atoms. For example, if you take water, so water is having more electronegative atom of the oxygen. So here it is a polar molecule. Take ammonia, NH3, so it is also a neutral ligand. So it is having more electronegative atom as nitrogen. So even though all these are neutral molecules, they are considered as a dipoles. Bond polarity is there between the corresponding more electronegative atom and the bonded atom. So that's why, so these molecules are neutral ligands, also considered as the point charges. So these point charges will undergo certain interaction, and according to crystal field theory, there is only electrostatic attraction or electrostatic force of attraction is present between the metal ion as well as the ligands. Both are point charges. Okay, that means whenever we come across about electrostatic force of attraction, which is nothing but generally the charges, like if you take ionic compound for example. So in the case of ionic compounds between cation and anion, we can observe the electrostatic force of attraction. So that means generally, so according to crystal field theory, this particular compounds or complex compounds are generally 100% ionic in nature. 100% ionic in nature. So that means this concept will try to explain the coordination compounds with respect to the point charges. And in order to understand this particularly, let us see about the sodium chloride, NaCl. For example, then go for the complex compounds. Once we understand this concept, then go in detail by considering the coordination compound. You take sodium chloride solid, NaCl. Solid, we are aware that NaCl is having FCC structure, face centered cubic lattice structure. So here the coordination number of Na plus ion is 6. That means every Na plus is surrounded by 6 Cl minus ions. Every NaCl is surrounded by 6 Cl minus ions. That means here around Na plus ion we can observe the negative charge in the form of the chloride ions. So this is negative field. This is the positive field. Positive field. So definitely, so now we can see this is a positive field and this is the negative field. So always this positive field is surrounded by 6 negative fields. And because of this reason, definitely this negative field will interfere with the negative field present in the Na plus ion. So where we get the negative field in the case of Na plus ions? Because sodium atomic number is 11. So by losing one electron it forms the cation Na plus. So definitely it is having 10 electrons, the Na plus. So those 10 electrons having negative charge, no? So they will interact with the negative field of the chloride ion, Cl minus. So because of this reason, there is interaction between Cl minus negative charge as well as the electrons present in the Na plus ion. So where exactly in the case of Na plus we have the electrons, especially in the valence shell, the electrons are present in the p orbital. That means the p electrons present in the Na plus ion will interfere with or interact with the negative charge of the chloride ions. So because of this reason, the p orbitals which are having electrons in the case of Na plus ion, they will slowly, or in presence of Cl minus ions, they will increase the energy. That's why in the case of the sodium chloride, so definitely the electrons present in the p orbital of the Na plus ion interfere with the negative field of the chloride. There occurs a repulsion. Because of this repulsion, the energy of the p orbitals or p electrons which are present in the p orbital gradually increases in presence of the Cl minus ions. So that's why always in Na plus, the energy of the p orbitals will be more in presence of the Cl minus ions. At the same time, we know that in the case of p orbitals, we have px, py, pz, where the corresponding lobes are present along the axis, whether it is px or py or pz. The corresponding lobes are present along the axis. So definitely the interaction will be always similar, whether it is with respect to px or py or pz. That's why the energy in the case of px, py and pz will increases to the same extent in presence of the Cl minus ions because of the arrangement of the corresponding lobes along the axis. And also be aware that this px, py, pz are degenerate because they have same value of the n, same value of the L. So definitely they are all degenerate in nature. This is with respect to how we can observe the interaction of the negative field on the negative field of the Na plus ions. Now let us take the coordination compound. As I told you here, in the case of the coordination compounds, every ligand is considered as a point charge, and also every metal ion is considered as a point charge. Between these two there occurs field interaction. Because of the field interaction, there is a chance, or simply there occurs the increase in the energy of the corresponding orbitals. At the same time, in the formation of the complexes, we have seen in the case of the VBT, valence bond theory, the involvement of the d orbitals, where it is inner d orbitals or outer d orbitals will generally participate in the corresponding reaction or in the coordination compounds. Okay, and here also, here coming to the d orbitals, we are aware that there are 5 d orbitals, which are dxy, dyz, dzx, dx square minus y square, dz square. So in these three, we can see the 3 orbitals are, we can see the double dumbbell geometry here, structure, where the corresponding dumbbells are present between the planes. And coming to these two, the dumbbells are present exactly along the axis. So these are axial orbitals. These are non-axial orbitals. Non-axial orbitals. Okay. Now all these have same value of n. You take a 3D series of elements, or 4D series of elements, and 5D series of elements. In the case of 3D, for example, so all the 5, 3dxy, 3dyz, 3dzx, and also 3dx square minus y square, 3dz square. So all these have same energy. That's why they are all degenerate. Similarly 4D, similarly 5D, all these, if you come across, the corresponding set of 5 orbitals are generally degenerate in nature. So they have same value of n, they have same value of L. So both the case, so because the n plus L value is same for all these cases, that's why all these are degenerate. And coming to the point here, we are saying here the metal ion is associated with the corresponding d orbitals, and ligands are generally negative, nothing but they are having the more electronegativity, or they will anionic ligands. So definitely they will interact with the electrons present in these orbitals. So I discussed earlier, previously, in the case of NaCl. So here also you can see here, so all the corresponding ligands definitely will try to interact with these orbitals. But in the case of p orbitals, the arrangement is similar. All the corresponding lobes are present along the axis. But this is a different case. because in these two cases the corresponding lobes are present along the axis, but here in between the axis. So that's why definitely there is a difference when you compare to the p orbitals. So whenever the ligand approaches the corresponding central metal atom of the ion, definitely there is a different kind of interaction with respect to these 5 orbitals, because all these 5 orbitals are not having same kind of arrangement. Okay, so that's why definitely there occurs splitting of these 5d orbitals. Splitting of these 5d orbitals generally will occur, but remember, in the presence of the spherical field, definitely, so the energy of all these generally 5 orbitals will increases uniformly. At the same time, in presence of the corresponding ligands, there occurs splitting of these 5d orbitals. So among these 5d orbitals, so definitely during interaction, definitely what happens is these 3 will split into one category. These are actually non-axial orbitals. These are axial orbitals. So in the case of octahedral splitting, if you come across, so generally these are actually called as T2G orbitals. These are called as EG orbitals. So in presence of the ligands, what happens is these totally 5 orbitals will split into 2 groups that we generally called as d orbital splitting. D orbital splitting. So because of the splitting, we can see here this becomes one set, T2G set. This will be EG set.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.